hyperplane fitting to a set of points. So there are formulations for this. You have AX equal to 0, basically the same formulation we have for that line, right? This is here. AX plus BY plus C equals 0. That can be represented by AX equals 0, right? How? By our X being a matrix where the first row is going to be our X's, second row are Y's, and then the third row a set of 1's, right? Then our A is going to be basically A, B, and C. And that's going to be a matrix multiplication together, right? That equals 0. That's a formulation of a hyperplane. So if I add to the dimensions, I can add to Z, I can add into 4 dimensions, I can add to 10 dimensions. It's going to be the same problem. So it's called a hyperplane. It's a linear regression. If you want to minimize this, which this is basically the sum of the squared residuals, right? You have this formulation to the power of 2. That is a matrix format. Minimization of this subjected to your parameter vectors having a normalized norm, or a norm equal 1. That means that your A2 plus B2 plus C2 equals 1. This problem, normally with hand, is very, very challenging to solve. But in terms of matrix algebra, it turns out to be a singular value decomposition problem, okay? Or an eigenvalue decomposition of the covariance matrix of your points. So the solution is actually the singular value decomposition of your X transpose, or by mean centering the X is actually going to be your eigenvalue decomposition. This is equivalent to what we call a principal component analysis. Formulation: calculate the covariance matrix of your observations. Then you have to perform what we call an eigenvalue analysis. Do you guys remember what an eigenvalue analysis is? Right? Lambda x is equal to Vx. X is going to be your matrix. This is going to provide you with a set of eigenvalues and eigenvectors that can now decompose your, for instance, in this case, matrix, which is covariance matrix, into a set of points, into a set of, vectors and eigenvalues. What that represents is what we call a principal component analysis. Essentially, it finds where the maximum to the minimum completely independent axes are going to be that represents basically from the maximum to the minimum variance of your data. Just to give you a practical understanding of this, what this represents is, for instance, this. Let's start with a line. You have a line here, okay? Imagine all of your points are going to fit exactly on this line. Let's say we don't have any type of errors, okay? What would be the variation of the data when you do orthogonal to that particular line? Is there any variation? No, so it's 0. What would be the maximum amount of variation that you're going to be seeing? Just think about it logically. Could it be in this direction? Orthogonal is in this direction. So that was the minimum, right? That was 0. So your points are in this line, right? So what direction would represent the maximum amount of variation of your data? Along the line, exactly. So that would be your second principal component. So you have one principal component for points that are exactly on the line, that if you do the calculation, which is basically the eigenvalue decomposition of the covariance matrix, would give you this. Say you have a set of points that are exactly on this line. This direction would give you basically the direction of the principal component that maximizes your variance. That is your largest eigenvalue. So the eigenvector corresponding to the largest eigenvalue would give you this direction. Conversely, the other one would be the smallest eigenvalue, because now you have only 2 in 2 dimensions. So what that means is that this direction here would give you the direction of the principal component of where you have the smallest variance in your data, right? That's what that is. Now, why is this in this direction? Why, if I go and I find the ion vector corresponding to this direction, why would that give me the best fit line? Why would that give me the ABC subject to A2 plus B2 plus C2 equal 1? Why would that provide that? Because this time we're not actually minimizing this. We're actually minimizing the orthogonal direction. So we're minimizing actually, if I were to do it this way, I don't have another color, but this one is what we are minimizing. We are not subjecting it to b equal 1 here. We're basically allowing it to roam free, and we have this as our normalization factor. That's why if we can actually decompose our variation into our principal components and in the direction of orthogonal, or the direction that has the smallest variation, that would basically give us the direction that would minimize the sum of the squared residuals that are orthogonal from any point to that line that we want. That's for line fitting. What about for planes? We have a plane here, okay? Do you have any variation in this direction? No. This is essentially the direction of our surface normal, right? So if we can find the direction of the surface normal, that is basically the direction that we have the minimum amount of variation, right? And that's actually, when you put the formulation there, that is going to be the case, right? N, we did it last semester, right? N times, x minus, x bar equal to 0. That's basically this formulation here. So if you can find the principal component that corresponds to the smallest amount of variation of a data point that is either planar or close to planar, this would be the direction it would give, right? That's why, and that would be our surface normal there. That's why we can utilize this formulation in order for us to basically identify the parameters of the best fit line or the best fit plane. We go and we perform an eigenvalue decomposition so that we can find the direction of the lowest amount of variation in our data set. And we do it on top of our covariance matrix, which provides the variation of our data set inside of a matrix. So this is the practical applied, basically, understanding of it, and there's clear mathematical background that actually goes and proves that as well. It's the same thing, right? Okay. So then you go and find the ion vector corresponding to the smallest ion value. Once you do that, that is going to be your parameter vector. For the intercept, if we are doing this, we're basically not considering this. We're basically doing these two. The intercept would be basically the mean of your points times basically the rest of A and B. Okay? It is possible to basically put a third basically column as well as 1 and perform this. It's not numerically stable. That's why we separate these as our two variables, and then we calculate the intercept separately. But if we want to do it this way, here directly, we can actually get the results of the C as a function of these two. Essentially, what you have to do is you put this as your least squares, basically as your Ri. You do the partial derivative with respect to C. What are you going to be getting? C is going to be 1. Then you're going to get this as a sigma. Okay, so it's going to be sigma A times xi plus sigma B times yi plus C times n. What does that give you? C equal minus A times sigma xi divided by n minus b times sigma yi divided by n. That is exactly that. Now you can fit planes, now you can fit lines, and everything in between. So I will leave you guys with this for the next session. And the residuals are basically calculated by this. I will just leave you with this, which is a step-by-step process and a step-by-step formulation. And I would like you to work with ChatGPT to understand what these are, and then build this as a function and bring it to next session, but the session after that we're going to be really focusing a bit more on this.